Hello and welcome to Eng Phys 3BA3 Lecture 9. We're going to look at the differential amplifier and then at a much better amplifier that does the same thing. So, difference amplifier we can actually analyze using BJTs. This is a circuit that has two BJTs in it, the way we've drawn it right here. This is called also the common tail differential amplifier because they both have the same tail here to ground. So we're back to the case where we have a positive Vs at the top and a negative Vs at the bottom. Here is the input and here's the output. Okay, so just for fun, if you like, you can try to analyze this ahead of time yourself. There's not really any tricks in it. It's the same circuits that we've done before, so go ahead. One catch is that there's two transistors, so if you assume the 0.6 voltage drop there, you can find the current, the emitter current for transistor 1. 0.6 voltage drop there, you can write the emitter current for transistor 2 in terms of VI2. These are both inputs. Your goal is to write the output as a function of the inputs and the supply voltage, as well as the resistors. So what are some variables you have there? You've got the emitter currents. You can say the emitter current is equal to the collector current for the purpose of figuring out the output there. You've got the output voltage, and you've got this VJ, voltage at the junction here. Okay, so you find this current in terms of that resistance and the voltage difference, and combine it with this current through R2 and the voltage difference, and then say that that's also equal to the current going through R3, which gives you another expression for VJ and VS. So once that's done, you've got one equation here, one equation there, one equation there, and one equation for this load line. Writing out what all of those equations are, you get four equations in the four unknowns, IE1, IE2, VJ, and V out. Solving those four equations gives you what the output voltage is in terms of the input voltages. And the usual case is that R2 is much less than R3, and the supply voltage is much greater than 0.6. And under that set of assumptions, you can simplify this to just say that the output is equal to this ratio of the resistances, R1 over 2 R2, times the difference in the input voltages, V1 minus V2, plus this offset. If we pick R1 over 2 R3 to be equal to 1, then we get rid of the offset, and it's just equal to the difference in the input voltage times this amplifier. So this amplifier is really good at detecting differences between one input and another input. This is a great thing to do because a lot of the time in the lab you've got a signal which is quite large and then often has a fair bit of noise in it. But if you can take the difference between that and some other signal that you say should be pretty close to it, then it's much better to do that in the analog world and then analyze things in a digital world after that. So suffice it to say for now that there's going to be times when you want to have a slight difference amplified. Okay, now if you actually were going to do this in some kind of an experimental setup for measuring, you probably wouldn't use BJTs to build this. You would use a much more robust set of BJTs like this to analyze it. This is the inside of the Texas Instruments LM741 op-amp. Now we're not actually going to analyze it, but you can see that it's made up of some difference amplifiers. It uses both NPN and PNP transistors in kind of a magic setup to have all kinds of amazing parameters. So this is a 6 input, 1 output device. The inputs are the difference input here, VI plus, VI minus, just like we were dealing with in the differential amplifier, the positive and negative supply voltages, and something called offset null. So the output is proportional to the difference in the inputs through some large gain factor, and if the input difference is 0, then the output can be offset through the voltages set at offset null. But most of the time we'll actually just ignore these pins. We'll say that those are just we're not setting an offset with offset null, and we've got the supply voltage fixed. We're not changing that as the circuit's operating, so we'll simplify this even further and look at it as a 2 input, 1 output op-amp. Most of the time we can assume that op-amps have ideal op-amp characteristics, which are the input impedance of both inputs, so this input and this input, are infinite. So really, not just really large, but infinite. So no current flows into or out of the input, either of the inputs. So no current can go in there, no current can go in there, or come out of those. The output impedance is 0. So the voltage is constant for all current. It would put out any current necessary to maintain that voltage. Really, these are sort of idealizations, and they're going to break down at some point. But for most circuits that we'd build with an op-amp, these are going to hold up okay. The voltage output is proportional to the difference in the inputs through beta. Beta would be the gain of the op-amp. This is not the same as the transistor beta. It's probably, as you can see by how many different transistors we've got, combining these and gain amplification stages, it's probably beta to some large exponent through the transistors, through the beta of the transistors that we're using to make the op-amps. So just take the beta of an op-amp to be very large, assume infinite. And the other thing is we're going to say that there's no delay in the output from changes in the inputs. In reality, a change in the input would take a little while to propagate to the output because of things like capacitors on the way in and transistors. There's some time that it takes for it to propagate through, but an ideal op-amp has no time delay. So it responds instantly. There's no phase change in the inputs to the output. It just amplifies right away. Okay, since the gain's infinite, another way to put this is that the op-amp is always in one of two modes. In the normal mode, the output does whatever it needs to make the difference between the inputs 0. Because if the difference between the inputs is not 0, then the output voltage is either positive or negative infinity, because the gain is infinite and the output is equal to the gain times the difference in the input voltages. So if you somehow force it to have a difference in input voltage, what's really going to happen is the output is just going to be the positive or negative saturation mode voltage, which is the supply voltage. So the output can't actually be larger than the supply voltage or lower than the negative supply voltage. 6.2, negative feedback simple amplifier circuits. Now let's look at how we could actually hook up an op-amp to get a non-infinite gain. Most of the time you don't actually want infinite gain, you want some specific gain. So let's see what this circuit does. The difference between the input voltages can't be anything. If we do have, suppose we do have some voltage here, which is higher than the voltage here, then the output would say, okay, we're going to produce beta times Vi minus Vi minus. So Vi plus minus Vi minus, so the positive input minus the negative input. And since the negative input is positive, this is a negative number, and so the output would be beta times some negative voltage, so it would be negative infinity. But then, if the output is negative infinity, we have negative infinity here, we've got some positive value here, so the voltage divider, no matter what these resistors really are, we're going to have effectively negative infinity here as well. So imagine the R's are equal. Then we've got positive 5 volts or something, and we've got negative infinity. And so if we meet positive 5 volts and negative infinity halfway, we've still got negative infinity. So attempting to put a positive voltage here, the output forces current, so it pulls so much current through R1 that it drops the input to negative infinity, or at least negative the saturation voltage. So this is an example of negative feedback. If we've got a positive voltage here, it'll shunt that down to cancel it out. And if we were to put a negative voltage here, the opposite would happen. Now we'd find that we've got negative on this terminal relative to this terminal. So the output goes to positive infinity, it builds it up, and then the voltage divider between like negative 5 volt input and positive infinite output is going to build that back up until the input is 0. So basically the input voltage difference is effectively 0. All right, that means that the voltage at the top here is the voltage at the bottom. All right, and so this is 0 volts here. Since this is a ground, that means the negative input is also at 0. And if this is at 0 and this is at Vi, we can find out the current going through this resistor. Now, where does that current go? You might think, oh, well, it could split through here and up there, but remember that the op-amp also has infinite input impedance. So that means that the current can't go through here, it's got to go up. So we can magically set this input to be at 0 voltage through hooking up the other one to ground and having this feedback, and also pull current through there, but then direct it somewhere else through the magic of an op-amp. So the current goes through here, through a voltage of V1 over R2, and then ends up being forced up this way. So whatever that current is multiplied by R1 is going to give us a voltage difference associated with from Ohm's law here. So let's make sure we've got the directions right. If the current is going from left to right, and the current is equal to I, then the voltage that would cause that would be 0, the side the current's going in, minus V out. Setting up those equations, we've got the current is VI minus the voltage at the minus 0, voltage at the negative input, and that's also equal to the voltage at the negative input minus V out. Since VI minus is actually 0, you can solve this and find that V out is negative R1 over R2 times VI. So this circuit is an inverting amplifier. It inverts the input and has a gain of R1 over R2. As long as V out is between the supply voltages, the analysis is consistent, and this works. So this would break down if we put in enough input voltage that the output is forced to be either the positive supply voltage or the negative supply voltage. Now the next circuit that we're going to look at is the non-inverting amplifier. This is a non-inverting amplifier with negative feedback. So we'll analyze it the same way. This is, since we set this terminal to VI, the negative terminal also gets put to VI. If it wasn't, if it was, let's imagine it was smaller than VI. Then the output goes to infinity and through the voltage divider pulls it back up. If this was bigger than VI, so VI is some smaller value than whatever this is at, then the output goes to negative infinity and pulls this back down. So either way, we are stuck with the negative feedback stopping us from having any difference in the input voltages thanks to that infinite gain of the op-amp. So that means that this voltage here is also the input voltage. So we've got VI on the negative input terminal as well. And that means the voltage divider between output and the negative input gives us V out minus VI over R1 is the current going down through here. Where does that current go? Can it go up into the op-amp? Nope, infinite impedance, so it must go down, which tells us that we've got this current is equal to the voltage divider across this bottom resistor. Solving for the output in terms of the inputs, we come up with 1 plus R1 over R2 times VI. So this is an amplifier as well, but it's not inverting. So we've got some positive number here multiplied by VI. Check your understanding. What's the minimum magnitude of gain for the single op-amp inverting amplifier that we looked at up here? And what about for the non-inverting amplifier? Well, here's the output in terms of the input. The minimum this could be, minimum magnitude would be 0 if we take R1 much smaller than R2, while for the non-inverting amplifier, the minimum magnitude is 1 because the resistor values have to be positive. So 0 and 1. In fact, if we set the non-inverting amplifier to a gain of 1, we come up with this circuit. This is the op-amp follower circuit. How do we get this to be a gain of 1? Well, we need R1 to be as small as possible and R2 to be as big as possible. In the limit, it looks like this. That's where we've just pinned the output to the negative terminal. Like the transistor follower, this may appear to do nothing but just output the same voltage as we're inputting, but it does do magical things once again to the impedances. So now we get the op-amps. This circuit gives us the magical properties of the op-amp to have infinite input impedance and 0 output impedance. So it'll maintain this voltage no matter how much current we're trying to draw out of it, and we will get we won't be able to push any current into it. So that means this entire circuit is keeping the op-amp properties of infinite input impedance and 0 output impedance. Okay, exercise 6.1. Now let's get some practice with these. For the non-inverting amplifier circuit in 6.4, here it is repeated, calculate the current through resistor R1 if VI is 1 volt, R1 is 100, R2 is 200. Show your answer doesn't depend on R1 as long as the op-amp output is not pinned at one of the supply voltages. So you need to find the current through R1. You'll do that by finding the output voltage by analyzing the op-amp like we did, or just looking up the result of that if you don't feel like analyzing it again, but it's kind of fun, so try to analyze it again. And then find the current through R1 from Ohm's law. Okay, so no current flows into the negative input, so we've just got VI over R2 is the current from looking at the bottom here. And so that means that the same current has to be going through R1, meaning the current in this particular case is 5 milliamps. Notice that we didn't have to use R1 anywhere, so it's independent of the resistor R1. This means it acts like a current source for R1. Exercise 6.3. Design a circuit using 2 cascaded inverting amplifier op-amps to make a non-inverting amplifier with gain less than 1, an active voltage divider, and then say why you'd want to use this instead of a voltage divider. All right, well, you may remember that the non-inverting amplifier had a minimum gain of 1, but the inverting amplifier didn't have a minimum gain. You could make its minimum gain magnitude 0 if you wanted to by choosing the resistors. So cascade 2 inverting amplifiers and find a way to make a gain less than 1. Well, you just the gain of an inverting amplifier is negative R1 over R2, so if R2 is bigger than R1, you can get a magnitude of gain less than 1. Using any combination of this for one op-amp and another op-amp, you can make the overall gain less than 1 in magnitude and positive by using 2 inverting amplifiers. And what's the point of this? Well, an imperfect voltmeter, so in other words, a non-infinite load, will not affect the circuit, so you can still have it'll maintain this voltage output due to the 0 output impedance of the op-amps. Exercise 6.4. Determine the output voltage as a function of the input voltage for the circuit shown in 6.3, the inverting amplifier, under the assumption that beta is not so large that we can take it to be infinite, but we are still going to assume that the input impedance is infinite. Show your answer becomes the same as our previous answer in the limit that beta does go to infinity. Okay, so the input voltage is 0, and we know that the output is beta times the difference in the inputs, which means the negative input terminal must be negative the output divided by beta. Saying the current that goes through here is the current that goes through here, we've got that V out minus the negative input terminal divided by R1 is equal to V negative input terminal minus VI over R2. Substituting our negative input terminal voltage in terms of the output into this, and then solving for the output voltage, you can come up with this expression, which sure enough, in the limit of infinite beta, is negative R1 over R2 times the input voltage. Voltage regulator. We looked before in section 4.5 at using Zehners as voltage regulators, but a problem is that the output voltage can't be varied. You're sort of fixed to whatever voltage the Zehner is made to break down at. But if we use an op-amp, so suppose we feed the Zehner's output voltage into this op-amp and then we vary the resistor ratio, we can get whatever gain we want on this op-amp circuit, and then get whatever voltage output we want too. So this can be used as a variable voltage regulator circuit. We still have the problem that the op-amp can't provide a large amount of current, even though it does have low output impedance. We'd need a high power op-amp to be able to run a huge amount of current through it. So this is better used as a voltage reference than as a real voltage supply for high power things. Non-ideal behavior in op-amps. So all real op-amps have gain that falls with increasing frequency. This is due to the capacitors to create low-pass filters to stop unwanted high-frequency oscillation. And the frequency behavior of an op-amp can usually be described in terms of a gain bandwidth product. So this is really a frequency where the gain falls to 1. Now, why is it a product? Because it's actually, so it's the product of the bandwidth and the closed loop gain. If you were to make a closed loop gain in your circuit, which is 1, so you suppress the intrinsic gain like we've been doing in say the inverting amplifier circuit by picking resistors so that the closed loop gain is 1, then you would find that the bandwidth where the op-amp does that, where your op-amp circuit actually gives you this output gain of 1, would be equal to the gain bandwidth product. So, for example, let's suppose that the gain bandwidth product is 1 megahertz. Then, if you then really at DC the gain is quite a lot higher. If you were to make a closed loop circuit that has a gain of 1, then as you start then it would behave like that up to 1 megahertz, right? If you go above a megahertz, though, then the closed loop gain you were trying to get of 1 is suddenly larger than the gain at that point. So the op-amp is going to behave like a flat frequency response up to 1 megahertz and then start dropping off. In reality, the gain has a frequency dependence that goes like this. So the intrinsic gain of the op-amp depends on the DC gain, its gain at very low frequencies, the current operating frequency, and the cutoff frequency, omega c.